Hi, kids. All right, now we're going to do a really fun problem where we actually get to apply everything that we've learned so far. We have two long parallel wires. They just happen to be, the current has to be going the same way. Again, it's not always going to be going the same way, so just, use your brain. But in this case, they are going the same way. 5 amps, 3 amps, separated by 30 centimeters. And we want to figure out the force exerted on each wire. Now remember that around any current carrying wire there is a magnetic field, and if you have two magnetic fields that interact, they will experience that's going to experience a force. So if I have a magnetic field around the red wire, a magnetic field around the black wire, I have two magnetic fields. Those two magnetic fields are going to interact, and so I'm going to get a force. So that's where I'm going with this. Okay. I would recommend that we try to find out, because force is a vector, so we need to find out the size and the direction. So let's do the direction first. Okay. Let's say I want to find the force on the red wire. Well, if I want to find the force on the red wire, there is a magnetic field there, but the magnetic field comes from the black wire. So I need to do my first right-hand rule. And so if I am on the right side of the black wire, I have X's all over here. Well, I don't care about the X's here, here, or over here. I only care about the X's where the red wire is. So I'm going to put black X's on the red wire, and that's to remind me that this magnetic field comes from the black wire. Okay? So now I have a current carrying wire in a separate magnetic field. So now I can do my second right-hand rule and figure out the direction of the force. To do the second right-hand rule, thumb points in the direction of the current. Your fingers point in the direction of the magnetic field, so my finger's pointing into the board, and my palm is pointing to the left, so the force acting on the red wire is going to be that way. Okay, so it's going to be to the left. If we were to do the force on the black wire, we already know, because of Newton's third law, that the force has to be pointing opposite ways, that's equal and opposite. But if we were to do this just to practice, I am on the left side of the red wire, so that the magnetic field is pointing out of the board all over here, so that I have to have dots every place. I'm not concerned about the dots here, there. I'm only concerned about the dots on the black wire. Okay? So now if I do second right-hand rule, I go thumb points this way, my finger points out of the board, so my force is going to be to the right, which is good because equal and opposite, so they are pointing opposite. All right, now I need to figure out the size. Well, and actually that means that the two wires would attract one another because they're going towards one another. All right, now I need to find out the size of each of these forces. So to do this, I'm going to be using my F equals BIL sine theta formula. And let's say I want to find the force on the red wire first. So if I do this, I'm going to get F equals, but my magnetic field comes from the black wire, so B, I'm going to make black, IL sine, and really it's going to be 90 degrees because the angle between this and this, 90 degrees. Okay? So BIL sine theta. All right, so if I do this, I first need to find out how strong the magnetic field is. So I'm going to again use the appropriate colors. B equals, and this is my mu naught I over 2 pi d. And if I do my formula, 4 pi times 10 to the minus 7th times 5 divided by 2 pi times 0.3, because I need to change this to meters. And if I do the math, I get, let's see, I want to make sure I'm doing the correct one, 3.33 times 10 to the minus 6 Teslas, and it is pointing into the board. Okay, so now if I want to find the force on the red wire, my force is going to be equal to 3.33 times 10 to the minus 6 times my current, which is 3 amps, times the length, which is 4, times sine of 90, which is 1, so I'm not going to worry about that. And if I do the math, I am going to get 4 times 10 to the minus 5th newtons and we already said it is pointing that way. Okay? Now, I have found the force acting on the red wire. Now, really, I wouldn't actually have to go back and do any math to find the force on the black wire, because I know that by Newton's third law they have to be equal and opposite. So the force on the black wire had better be 4 times 10 to the minus fifth newtons pointing to the right. But if we go back and we just check it to make sure that we're correct, let me do the math real quick here. So if I'm going to do, so I know this is, let me put my answer for this one right there. But if I go back and I check just to make sure I'm doing it right, so I'm going to have F equals, my magnetic field comes from the red wire, IL sine 90. So I got to solve for B first, which is going to be 4 pi times 10 to the minus 7th times 3 over 2 pi times 0.3. Do the math, I get 2 times 10 to the minus 6 Teslas, and that is pointing out of the board. So now, plug my stuff in, 2 times 10 to the minus 6 times my current, which is 5, times the length, which was 4, times sine of 90, which is 1, and if I do the math, I get 4 times 10 to the minus 5th newtons, and it is pointing this way. So as you can see, Newton's third law holds up. Hooray, hooray. Bye, kids.